Okay, so let's start with our problem, our nice simple warm-up problem. Partial squared, partial x, partial y. So this means second order derivative because of that 2 there. We're going to take a derivative once with respect to y, once with respect to x. There's this long function. I won't say it all out. This notation says to do what? Plug in. You're evaluating it. And our options are 1, 2, 3, 4, or 5. What's the answer? Two is the answer. Now what happens? Well, if you're going to take a second derivative, you've got to take a first derivative. So let's take the first derivative with respect to y. Now you'll notice I marked things which have y. Those things will actually have derivatives happen. Things without y, how are we treating those terms? Constants. So this big expression goes completely away. This just copies down. And okay, it's easy to take these derivatives. Now, remember, we have to plug in at the end. But we can plug in at any time when it's possible. Since we've already taken a derivative with respect to y, there's nothing else we're going to do where we need to have y kept as a variable. So I can plug in y equals 1 right away. Say, I want to work in that slice. Now you might say, well, why do that? What happens when you plug in y equals 1? You get 0. There. So your function in that slice looks like 2xy, or really 2x times 1, which is 2x. So the partial derivative of that is 2. And you plug in 1, you get 2. All right. So there we go. So what's today? Well, the good news is we already talked a lot last time. We're getting to the idea of differentiability. So differentiable, in some sense you say, well, differentiable says I can take a derivative. Well, yeah, that's kind of what the word means, but of course that doesn't feel like a really good definition. So for me, I like to say differentiable says locally I look flat. Now, for functions of a single variable, when you zoom in, you look like a line. For functions of 2 variables, you'll look like a plane. Now, when we go back to Calc 1, we say, well, differentiable means I can take a derivative. And so there was this sort of notion. It's like, okay, if I can take a derivative, I locally look flat, life is good. It's not quite that easy for Calc 3 here. So it's not enough that the partial derivatives exist to be flat. So what do I mean? Well, there's this particular function here. Z equals the square root of absolute value of x times absolute value of y. This is a perfectly defined function. It's defined everywhere. And now we say, well, what's happening at the origin? Well, if we think about sort of the intuition, we say, look, if I want to know partial derivatives, let's suppose we want to look at partial f, partial x at 0, 0. Let's say that's our goal. So what does that say we do? Well, what we do is we want to work in the slice. So here we're going to take the y equals 0 slice. All right, well, where is that? X, y, z. And the y equals 0 slice is that slice right there. Now, what is the function doing if y equals 0? What's the value of this function? 0. It's always 0. You say, okay, when I look in the slice, I see that. So if I see that, and I say, okay, what's the derivative of this constantly 0 thing? The answer? 0. I say, okay, well, that's nice. But now, suppose I want to take a look not at partial f, partial x, but partial f, partial y at 0, 0. Well, again, we're going to work in a slice. This time it's the x equals 0 slice. So that's the slice we want to focus on. So that's this slice here. Now, if x equals 0, what's happening to this function?
0.
It's always 0. So in the slice, I see, oh, it's always 0, so the derivative will be always 0. So now it says, oh, it looks like in the x direction I look flat. By that, I'm always 0. In the y direction I look flat. It means like I should always be 0. So intuitively, that says, oh, this, if it were differentiable, we would look like the xy plane. But do we look like the xy plane? And the answer is no. I'm not a particularly great artist, but what's happening here is it's being crimped. And let's suppose instead of trying to do a bad drawing, the handout has a better drawing, somewhat better drawing. Let's suppose I try to do the following. Let's look at a different slice. So what about the slice x equals y? Because I can look at other slices. Now, I'm not talking about any derivatives in this case. We'll save that for a different day. So I'm looking at a different slice. In the slice x equals y, what do I look like? So if x equals y, what happens? Well, what does the function z look like? Z looks like, okay, if x equals y, then instead of thinking of it as absolute value of x times absolute value of y, let's just think of it in terms of x. What would it be? It would be x squared on the inside, but then what? Square root of x squared, which is absolute value of x. So in that slice, what you see is something that looks like a V shape. And no matter how much you zoom in, that's not going to be flat. So that's why I say there's a crimping going on here. So you have to be careful. So it's not enough that the partial derivatives exist. You need just a little bit more, and not very much more, because it's on the screen, if you have partial derivatives and they're continuous. And basically, being continuous says, hey, things look nice. Continuous is a fancy way of saying nice. So continuous, nice. No surprises. So if you have your partial derivatives and they exist and are continuous near your point, then it is true that you are flat. Now, good news, we are going to deal with functions which are nice. So you're not going to have to stress like, oh no, am I differentiable or not? No. We won't have to stress about that. We'll have other things to stress about. Okay, so why is that true? Well, what I can think about is I can take f of xy minus f of ab. And let's just start with that as a given. And okay, so f of xy minus f of ab. Well, what I can do is I can add and subtract a term. So notice I've subtracted f of xb, I added f of xb. So those two terms would cancel. So you still have f of xy minus f of ab. All right. So I haven't really done much other than I've added 0. But not just any 0. A well-chosen 0. The second term perhaps is a little bit easier. And you say, well, I have f of x comma b minus f of ab. And the claim is, well, that's about f sub x of ab times x minus a. All right. And why is that? Well, Do you remember why this is true? This goes back to the idea of tangent lines. So if you remember tangent lines, they're basically good approximations nearby. That's the spirit of tangent lines. Because we zoom in, things look flat. The flat thing is a tangent line. And so if I have your function, so let's say this is g of x. And then I have my tangent line here, a. So my tangent line looks like what? Well, it's y equals g of a plus g prime of a times x minus a. Or, put another way, this y, I can say, well, that tells me that g of x, which is the function, is approximately g of a plus g prime of a times x minus a. Or g of x minus g of a is approximately g prime of a times x minus a. So the change of the function versus the function nearby versus the function at a is about, take g prime of a times the change in x. What's happening here is this f of x comma b is acting as your g of x. So g of x minus g of a is about g prime of a times x minus a. So this is tangent lines. This just says, oh, hey, I know that in the slice, the tangent line is a good approximation. Okay, that's the idea. That's the spirit of it. All right. Well, same thing for this part. F of xy minus f of xb, it's about fy x comma b, y minus b. And this is in the slice x equals a. However, because things are continuous, if I'm in the slice x equals a, this is in the slice where x equals x. Here's the slice x equals a. X is close to a, so these are close. So that's why you still get this approximation. And the big punchline is the following. The function f of xy is approximately, move the f of ab across, so the value of the function plus how quickly are you changing in the x direction times the change in x, plus how quickly are you changing in the y direction times the change in y. So that's sort of the big idea. And today is just variations on that idea. And not just today, but the next couple of days. So what is this right-hand side? Well, one thing that we'll call it the linear approximation. Linear because it's a flat thing. There's no power of x, there's no power of y, there's no x times y. We'll also call it the tangent plane because it's a plane. If you say let z equal this, it's just another way that you could rearrange and write a plane. So it's the tangent plane. It's our flat object. We say the function is differentiable. It should be locally flat. You say, well, what's the locally flat thing? This is the locally flat thing, the tangent plane. All right. So let's see if we can draw any questions. Okay. So we have our function, z equals f of xy. It's a surface, and I've marked here a point AB. I just want to sort of build up geometrical intuition about what's going on. So you zoom in, it looks flat. So there's this flat thing here that touches that surface at that point. And the value of this point here, this height is at z is f of a comma b. So the f of ab is how high up you are. Now, we talked about this last time, we can work in slices. If you work in the slice where x equals a, which is this red slice here, then you'll have a curve. So your surface becomes a curve. What does your tangent plane become? The answer? Becomes a tangent line. So the tangent plane that we have over here, when we slice, becomes a tangent line. And now, what is that tangent line? Well, it should be the case that it should be the tangent line here, right? So this is still your f of ab. So z equals the value of the function, all right, that matches, plus the derivative. Well, the derivative would be partial f partial y. So that's why it's f sub y times y minus b. Does that match with what we'd expect it to be true? What happens if you plug x equals a into this expression? Plug x equals a into this long term, what changes? Yeah, this middle term goes away. And you get f of ab plus f sub y of AB times y minus b. Exactly what we say it should be. Well, that's good. That tells us that the slice does what we think it should do. In other words, when you slice this plane, you get this tangent line. All right, so that's this tangent line we just talked about. But we could also look at this yellow slice here. Say, okay, well, that yellow slice, that's y equals b. And then we have this curve. And now it's a curve as a function of x. It's a function f x comma b. You say, all right, well, what happens if you slice the tangent plane? Well, you get a line. And it'll be the tangent line. Again, this right here is the height f of AB. So the tangent line would be the value of the function, that's f of AB, plus the derivative f sub x of AB times x minus a. Now, we're in the slice y equals b. Come up here, plug in y equals b into your tangent plane. What happens? The last term disappears. And so this becomes our tangent line in the slice. So, all right, good. So in some sense, this matches with what we expect. We have our tangent lines in our slices, and that more or less helps us figure out what the plane should be. So I like to think of it as this f of AB, it's like moving us up and down. Then you have tilt in one direction, f sub x, and a tilt in another direction, f sub y. And combining all those actions together, that can get our plane. Now, one quick note. If I look at these pieces right here, f of AB, f sub x of AB, f sub y of AB, what do all of these terms have in common? They have AB in common. Yes, that's true. What else can you say about these terms? And I'll warn you, I'm not looking for anything hyper profound. Well, someone said they're functions. Almost. But not that. What are they? You shouldn't think of these as functions. What should you think of these as? These three pieces are all numbers. Yes? Because you've plugged in. You have to evaluate, right? F of xy is a function. But when you plug in x equals a, y equals b, it's now a number. It's a function where you've evaluated. So this is a number, this is a number, and this is a number. So these should all be numbers here. So don't put down, a tangent plane should be a plane. So if you write down a long, complicated expression with lots of variables, that's not a tangent plane. So keep that in mind. All right, so that's the theory. Any questions before we get to the practice? Okay, the practice. Find the tangent plane to the surface z equals x cubed plus 3xy minus 4y squared plus 6x minus 2 at the point xy equals 1, 1. So in particular, we are thinking about this part here. This is our function of x, y. So we have z equals a function of x and y, and we're saying, okay, what's the tangent plane at the point where our inputs are x equals 1, y equals 1? So let's talk about what happened. So there's a couple ways to write it. Because I'm thinking of tangent plane, I'm just writing as z equals. Now, what's the key? We have our function. We say, well, if I'm going to make the plane, I need to know what the function is. I need to know the partial derivative with respect to x and the partial derivative with respect to y. So step one, take your partial derivatives, because you need to know how things are changing if you want your tangent plane. But remember, we need numbers here. So we are going to plug x equals 1, y equals 1 into all three of these functions, which gives us the values of 4, 12, and negative 5. And then we plug in 4 for f of ab, 12 for f sub x. A is 1, f sub y is -5, b is 1, and we can either write it as z equals 4 plus 12 times x minus 1 minus 5 times y minus 1, or z equals 12x minus 5y minus 3. There are reasons to write it in these ways versus other ways. In particular, we're going to get into next week where this idea of like we want to use approximation, and when you want to do approximations, you want to keep it in that form. But in terms of would you get points, both would get points. And there's other ways. You can move the z across, move the 3 across, as long as you have your plane. All right. So we know we can find tangent planes. Good. But now, what else can we do? Well, for something a little different. We're going to talk about the chain rule. Okay, so the chain rule, it's a really great rule. It's probably the best rule when it comes to differentiation. And the idea is you have a series of variables which build off of one another. So we have, in our most basic case, suppose we start with z as a function of x and y. And we'll say x, that happens to depend on a variable t. And y, that happens to depend on a variable t. So I formed a structure here. I like to call this a tree. And for people who are in computer science, they'll know, yes, trees go down. But at the top, that's our variable. We say, well, z, what does z depend on? In other words, what's z a function of? Of x and y. So I say, well, it's of x and of y. So I have these two branches to indicate what it depends on. What does x depend on? Just a single thing. So I write one branch down, t. What does y depend on? Just a single thing, t. So this shows how all the variables connect in terms of what depends on what. Now, we can look at this and say, well, you know, ultimately, z only depends on t. Because if I know t, that tells me the next layer up, which tells me z. Since z is a function of t, I might want to know how does z change with t. In other words, I'd want to take a derivative. So this is where we talk about the chain rule. So we have functions inside of functions. In other words, you could think of this z equals f of x, y. We could also think of it now as z equals f of x of t, y of t. So how are we going to do this? Well, we start with our linear approximation, which we just figured out. And we say, well, f of xy minus f of ab, that's f sub x of ab times x minus a, f sub y of ab times y minus b. And we say, okay, so we have this linear approximation. We start thinking about our pieces. Well, this x minus a, that's pretty easy to see what's going on. A was the x value we're taking our approximation at. X should be a point nearby. So x minus a, change in x. Y minus b, similar idea, change in y. So that when you see this delta, then so we don't say triangle x, triangle y, it's delta x. Delta y. Delta stands for small change in. So change in x, change in y. Here, on the left-hand side, we see fxy minus fab. That's changes in our output. Now, our output variable is z, so that's delta z. And then finally, our partial derivatives, well, f sub x, that's how z changes with x, and f sub y, that's how z changes with y. All right, so linear approximation can be rephrased in this context. Now, the idea, divide everything by change in t, and we have this expression here. And now, the last aha is as your change in t gets small, then what will happen is your discrete changes, delta z over delta t, become your instantaneous changes. It becomes your derivatives, dz dt. This approximation, it gets better and better, and so it becomes an equality. Similarly, delta x over delta t becomes dx dt, delta y over delta t becomes dy dt. So that we have this formula. dz dt is partial z partial x dx dt partial z partial y dy dt. All right, so that's a very simple case. And it makes sense. Now, how do you do this in general? Here's the idea. Draw a tree which shows the dependencies of your variables. So let's suppose we'll do something a little bit more complicated. So we'll follow this procedure here. So suppose I say, look, I know that z is a function of x and y, but x, now it's a function of not just one variable, it's a function of two variables. And y is also a function of two variables, s and t. So suppose this is my relationships. So what's at the top of our tree? Z. What does z depend on? X and y. So we draw x to y. Then we come to x. What does x depend on? S and t. What does y depend on? S and t. It's okay to have repetition. You're just drawing a tree structure down. You're not trying to form loops, just complete tree structure down. Now, step 2. Find all the paths from the top to the variable we're taking the derivative with respect to. So let me go back and point out what happened here. In this case, we wanted to know, how does z change with respect to t? Well, how many ways can I get from z to t? There were 2 ways. So I had to have 2 paths. You say, okay, so let's, over here, suppose we want to find, let's start with, do you want to start with s or t?
T.
S. All right, so I heard s first. Now, suppose we wanted to find partial z partial s. I'm going to pause for a second. Why did I use a dz dt here, but a partial z partial s here? Was that a mistake on my part, or did I do something right?
Because the place where the s is where the t would be if you had instead chosen t.
Okay, so I could have chosen t here. So what does that tell me about z? You're right. I could have chosen a t here. That tells me something about z.
It doesn't only vary in terms of s?
Yeah, so z varies with multiple variables. So there are multiple things I can change. So you use partial whenever there's multiple things changing. When do we use the d? Well, there's only one thing that changes. See, ultimately, t determines everything. So that's why I only had one variable. So you use the d for one variable functions, use partial for multivariable. Would we dock you points? Probably not. But some graders are mean. So they might. So you just want to be careful. Okay, so partial z, partial s. How many s's do we have? We have 2. So how many ways are there to get to those s's? Well, we have these 2 paths through x and through y. Okay, so that's defined. Now the next step. It says for each path, there's a sequence of partial derivatives. So coming back here, I'm trying to understand how z changes. So z depends on x. So really, this says, if I want to understand, I have a partial z partial x with this edge. Similar, I have a partial z partial y for this edge. So if I want to know how does z vary as I vary y, well, that's partial z partial y. This edge, x to t, would be a dx dt, and this edge would be a dy dt. So every edge is a derivative. This edge from z to x, what do we put down? Partial z partial x. This edge from x to s, what do we write down? Partial x partial s. How about x to t? partial x, partial t. And we're using partials because multiple variables. And so every edge, it's a derivative. The top, it goes on the top. The bottom goes on the bottom. So I'll just keep writing this in. So every edge has a derivative. So here we go. Now we have a path. And for each path, we multiply. So I can really say z depends on s in two ways. So there's two effects. So to get the partial z partial x, I have to really, partial z partial s, I have to combine the effects. So I first say, well, how does s affect z through x? So that's on this path here. So it's partial z partial x, partial x, partial s. I'm following the path down to s. And then I add to that the other path. How does s affect z through the variable y? Partial z, partial y, partial s. And so for each path, we multiplied the edges that are associated with each edge, so associated with the derivative, and you add up all the results. That's the idea. Okay, so what if I asked for partial z partial t? What would that look like? Aha, someone was like, Steve, just copy. Just change s's to t's. And essentially, it's a similar idea, right? Because what's going to happen is now you have similar paths, except you just branch in a different way. So it would be partial z partial x, partial x partial t, plus partial z partial y, partial t. Okay, so this is the idea of the chain rule. And oftentimes, people often wonder, well, do we really need all of this? Couldn't we just say, well, if I know what z is as a function of x and y, and I know what x is as a function of s and t, I know what y is as a function of s and t, couldn't I just plug all this in? And then couldn't I say, oh, look, I have z as a function of s and t. Life is good. I just ignore all this intermediate structure that's confusing me. And yes, if you have all that information, but sometimes you don't. And so that's why we have this extra structure that we're adding in to handle that. So how might we ask you such a question? Before I go to the next part, let's handle questions. Yes?
Is this a way that you can do it, or would it be, are there errors? Can you think of it like unit cancellation, like you're canceling out the bottom, like the top divided by the bottom, so like
the partial x's cancel, the partial y's cancel. Can you think of it that way?
Or is that?
It's vaguely like that.
Is there room for
But you know, you might say, well, wait, then you have two partial z partial t's. How does that get you to just the one partial z partial t? And you can almost think of it like that, but what I like to think of it as is this is helping me understand how is z changing with respect to t. Well, here, this is the change through x. So I'm recording, it's going through x, then through t. This is the change that corresponds to the y. Going through y, going through t. Okay. Other questions? All right. Well, here's a problem. Now, this is a problem from an old exam. We cannot ask this problem on current exams because we've enlarged the font and this would no longer fit. So we have to make them more interesting. But we still like to ask these kinds of questions because this is a good test of do you understand the rules, or do you just get intimidated by there's too much going on here? But we don't want to be intimidated. we want to solve these things. We want to be able to figure these things, work them out. Okay, so given that f of xy is a function u of xy, v of xy. So we have f of xy depends, is a function g of u of xy, v of xy. Okay, so what do we have going on here? Well, if we think about what's going on, we could draw a tree here. So let's suppose we put on our tree, we'll have g. What does g depend on? U and v. What does u and v depend? Well, what does u depend on? So u depends on x and y, and v depends on x and y. So we have our nice, lovely tree here. So we can mark our partial derivatives. And here I'm going to use the subscript notation just to have some sanity. So we have g sub u, derivative of g with respect to u, g sub v, derivative of g with respect to v, u sub x, u sub y, v sub x, v sub y. All right, there's our tree. Now, what are we after? We're after f sub x and f sub y. So we're trying to take the derivative of this with respect to x. So we're really saying take the derivative here with respect to x. So if I want to find f sub x, I'm going to this structure here, and I look for the x's. I see there are two of them, so that says I'm going to have two terms. According to the chain rule, what will fx look like generically? Well, work your way down. Gu, u sub x. Derivative of g with respect to u, derivative of u with respect to x, plus g sub v, v sub x. All right, now we're after f sub x at a very particular point. Okay, so let's make some notes here. If we want fx at 1, 2, well, this is telling us here x equals 1, y equals 2. What can we say about u? What does u equal? Can we figure that out? Well, what does u depend on? X and y. So I can plug in 1, 2. Do we know what u of 1, 2 is? We come over to the right slot. U of 1, 2 is 2. Do we know what v is? Well, plug in, because v depends on x and y. V of 1, 2? -3. All right. So, why do I point this out? Because what do we have? We'll have g sub u, but notice g sub u is a function of u and v. So if I want f sub x at 1, 2, that'll be g sub u at what point? U sub x at what point? G sub v at what point? And v sub x at what point? U is a function of x and y. So these should be the xy coordinates going into u. So what's the right point for the u sub x? 1, 2. How about the v sub x? Also 1, 2. What about the g sub u? Well, g sub u depends on what? U and v. So what goes in here? 2, -3, the uv. All right, do we know g sub u at 2, -3? G sub u, 2, -3, 4. Do we know u sub x at 1, 2? Well, here's u sub x, 1, 2. 4 times 1. Do we know g sub v at 2, negative 3? Negative 2. Do we know v sub x at 1, 2? Negative 1. So what do we end up with? 6. Now, in the interest of time, I won't do the other one, but it's a similar idea. But what do you notice about this table here? You're not using much of it. So this is as much of, do you know the right ideas? All right, now we don't have time to do our last multiple choice, but I know I skipped the thought for today. So let's do a quick thought for today. If you always do what you've always done, you'll always get what you've always got. There's another one that's often attributed to Einstein. You know, the definition of insanity is expecting to do the same thing but get different results. This is a time to reset yourself. Reset what you're doing. If you have not gotten the results you like, you shouldn't keep doing what you're doing. You need to change. Get yourself better results. You can do that.